Okay. And well, I would like to say some words to Frank. So when I was undergraduate student, Laura suggested me to study her work with Ernesto Rosales and Sergei Voronin about the analytic classification of non-dicritical vector fields. And she told me that in that work there were some constructions that was inspired by a beautiful work of Frank Loray. So thank you, Frank, for your beautiful work, and bon anniversaire. So I'm going to talk about on the geometry of the semimodule of plane branches. So the aim of this talk is try to say that what I understanding about the geometry of the semimodule. But the semimodule is an analytic invariant of plane branches. So a plane branch, let's see, be a plane branch that is so it's the term of an analytic curve. So this is with f an analytic function into variables, and 0 equals 0, and f irreducible. So we say that if we consider C and D be plane branches, we say that C and D are analytical equivalent if and only if there exists by holomorphism such that this biholomorphism sends one of the curves in the other. Okay? And important remark, that is analytical equivalence implies topological ones or equisingularity of the branches. Okay? So in the 1960s, Zariski was interested in the description of the moduli space of these branches. So he was interested in the description of the quotient space. We fix we consider C a fixed plane branch, and we denote by EC the equisingularity class. That means all the plane branches equisingular to C, and he was trying to describe the space, the quotient space under analytic equivalence. Okay, so that's the main goal. And now I'm going to introduce some invariants. So topological. Here is the semigroup of the branch, and analytic. So here is the semimodule of the branch. So the semigroup is defined. So this is the semigroup. And it's defined as the set of multiplicity intersection between the branch C with the other analytic branches. Analytic curves, sorry. And the multiplicity intersection can be understood as if we consider, for example, I'm going to take the cusp and the yx this is I think, a more realistic row. So if you take the cusp and the yx, you make a perturbation because in the origin the intersection is not good. You take a little perturbation, so we have now 2 points where the intersection is transversal. So this is meaning of the intersection multiplicity. So also this can be computed as no, here this analytic curve can be reducible. Yeah, there are all the analytic curves. If you take D equals C. It's infinity, but it's not important. It's not important. And this can be computed as the following way. It's another way to compute. Where phi C is a Puiseux parametrization of the branch. Okay. So this is the semigroup. Okay, so this is a subset of the non-negative integer number. So now the semimodule is defined in more or less the same way as the order of in the following way. So now we take holomorphic one forms in dimension 2. We take the pullback under the parametrization of the curve. This is a holomorphic one form in one variable. So we take the order of the coefficient of this one form plus 1. So this is also a set of the integers. And we have some properties about this set, and the main one is, well, I will denote this order plus 1 as this for the differential value of the one. So some properties about this set is this is an analytic invariant of the branch. Okay, Another property is that the semigroup minus 0 is contained in this semimodule. Sorry. Yes. Yep. And the third one is this property about if you take an element for all the elements of the semigroup and the semimodule, you take the sum. This is contained in the semimodule. Okay. So another, or where a nice property about this semimodule is this is finally generated, and is an important property that we can write, or we can decompose the semimodule in the following way. So we can write we can describe this semimodule where lambda j is for j1 and s. And an important property is that lambda j does not belong to this set that is the union don't belong to this union. Okay, that is a decomposition of the semimodule. Okay, and these elements are the basis of the semimodule. Okay. So okay. So the definition. So an standard basis of C is a list of holomorphic one forms such that the differential value of the branch with this holomorphic one form is precisely lambda j. So, and what is the problem about the geometry? So what I'm thinking about the geometry is try to describe these elements in terms of the foliation defined by them. Okay? So the question is, we can characterize omega j in terms of the foliation defined by in terms of the foliations. I'm going to explain what I'm thinking about this. So, from now, I assume that C has an only Puiseux pair. Okay, and in this case, lambda minus 1 is n, lambda 0 is m, with n the multiplicity of the curve, and m is the first characteristic number. And obviously, well, I assume that m greater than n greater than 1, and the greatest common divisor is 1. Okay? Now, so I'm going to talk about foliations. In specific, I'm going to talk about the totally the critical foliation. Okay, and I'm going to talk of this foliation with an example. So let's consider if the foliation generated by this holomorphic one form. Okay, with n and m satisfying these properties. Okay, so the origin is a singular point and is not a simple singularity, so we can desingularize the foliation, and the desingularization is given in the following way. So the origin is a singular point, so this is a real picture, and we take the sequence of blowing ups given by the Euclidean algorithm of n and m. So this is a sequence of blowing ups. And we compute all the sequence, 1, 2, k. And in the last one, so we obtain the critical component that is a irreducible component of the exceptional divisor that is transversal to the foliation. Okay? So all the leaves got transversalities. So P is the composition of these blowing ups. That is determined by the Euclidean algorithm of n and m. Okay? And note that in this example, there are no singularities, the intertangency points in this component. Okay? So a definition is a definition. So we say that a singular foliation is totally dicritical foliation, okay, if satisfies that the strict transform by the sequence given by the composition of this blowing up has a dicritical component in the last one. So I will denote E. This has a dicritical component and is the component E that appears in the last one. And there are not singular points. There are not singular points. Neither tangency points. On this component. So as in the example. In the example, there are no singular points, neither tangency points in this component. Okay? So we say that a foliation is generalized totally dicritical foliation if F satisfies 1 and 2 and 3, 4, 5. So 3 is the unique dicritical component. Is the unique, I don't have time.
Can you state the result? We are almost gone. No, you have a pair of minutes, 5? Okay. We make a translation.
Okay, five is
okay.
Is
4.5. Yes.
Oh, okay, 4.5. 4.5. 4.5 is good. Is the unique dicritical? Okay. Pi is the minimal reduction of singularities. And there are not saddle nodes. Okay? So what is the result? Okay? So here so the first one is my PhD thesis. So let's see a plane branch with semimodule given by, so this is generate, this means that these one are the generators, okay? So in my PhD thesis, I proved that lambda 1, so here is n, here is m. So lambda 1 is the maximum. Well, assume that s is greater than 1. So this is the maximum of the differential values where omega is analytically equivalent to this one. Okay? And Cano, Felipe Cano, Nuria Corral, and David Senovilla in 2023, they proved that lambda j is the supremum of the differential values of omega j, where omega j satisfies that the divisoral value is Tj, where Tj is can be obtained in a combinatorial way of the semimodule. This can be obtained in a combinatorial way of this, and they prove that if you take if omega satisfies that the divisoral value is lambda j, then the divisoral value is Tj. Okay? So, but the work in progress is, well, this is good because we can prove that the foliation defined by these omega j's are totally the critical foliation, but the climb is the stronger one. There are generalized totally the critical foliation. So the resolution is given by this. Okay, that's all.